Welcome to geometry. Today we want to take a really brief look at section 9 of our text, which is on proofwriting. And there's nothing to fill in this section, so it's just going to be a relatively brief discussion on the 4 or so pages that there are there. I would encourage you to read through these pages yourself and to look at them. My expectation is that you are all familiar with proofwriting, but I'm going to highlight a couple of differences that we're going to try to do for this course. This might help cement some of the ideas of proofwriting for you if you have not been comfortable with proofwriting in the past. So for now, we'll go ahead and just discuss what we have here in this section on proofwriting. So the biggest thing is that in the past we've done proofwriting, which is mostly done in a prose style. So just saying what we need to say, justifications within our statements, no action with a reason for that action. It's not split up. So let me try to clarify that a little bit here. What we're going to do in this class for many of the proofs is a 2-column proof. The 2-column proof looks exactly like that in the example below. We have a column which gives the action that we're doing, and then we have a column which gives the reason for the action that's done. In this case, all of the actions are numbered, or those things that associate to a particular reason or justification. So this is my statement that I'm making, and this is the justification. So for this particular example, if x and y are odd integers, then x plus y is even. Notice this is an if-then statement, also written as P implies Q. So this is just a conditional statement, if-then. So if x and y are odd integers, that's what we're assuming to begin with. That's the given. We're given that x and y are odd integers. So you should always start with what's given. All right. So once you have what's given, then you start to make some statements. Well, if x and y are odd integers, then we know that x can be written as 2k plus 1 for some integer k. And y can be written as 2l plus 1 for some integer l. Why can they be written that way? Well, those are just the definitions, or that is the definition of an odd integer. So I can write them this way because that's the definition of an odd integer. Well, what can I do with those? Well, x plus y, right, this thing that we're trying to make a statement about, is equal to this thing. How do I know that those are equal? Well, because of the addition property of equality, right? X is equal to something, y is equal to something. So when I take x plus y, I get that something plus the other something, okay? Addition property of equality. So then when I move down a line, what I've done is I've simplified. So what did I do here? Well, I performed the addition, right? 1 plus 1 is 2. Fantastic. Well, the distributive property allows me to factor, okay, because these two things are equal because of the distributive property. So moving down to here, I get this line because of the distributive property. Well, what does this do for me? Well, let's say, well, k plus l plus 1 is an integer because the integers are closed under addition. And then this here, all right, noticing that it's 2 times something, we can say that x plus y is even because we have this statement where that's an integer, and that is the definition of an even integer. So we started with our assumption and we ended with exactly what we wanted to find. X plus y is even. So assume this part and show this part. P implies Q. P is x and y are odd integers. Q is x plus y is even. Okay, so this, again, this is a two-column proof. So this is a little bit different than what we may have done in the past. It's not different in terms of overall we have a different approach. It's different in terms of these are the things that exactly what we would have written down in a prose style proof, right? But we wouldn't have these written down because we would assume that the reader is capable of understanding that. Okay, so in the proofs that we've been writing in previous courses would just look like this on the left-hand side with the right-hand side gone, right? No numbers, this is what we would have, and all of these justifications would be gone because this is left to be understood by the reader. For these proofs to help us out, to make sure that we have solidified our understanding of a proof, we're going to do two-column proofs. What we're doing and a justification for what we're doing. Excellent. So, yep, excellent here. So a little bit of a comment on when you're doing algebra in a two-column proof. You might have a given statement, and then you might want to perform some algebra. So here we have 3 times 2a plus b is equal to 2 plus 3b. We're saying that's given for this example. Now, if we wanted to do all of the algebra steps and justify all of them, well, we could apply the distributive property, distribute the 3 in, and then we could subtract 3b from both sides because of the subtraction property of equality. And then we could divide by 6 and find the value of a by the division property of equality. Well, gosh, that was a mouthful and it took forever to explain. Okay, so instead of doing all of that in a two-column proof, what we'll simply do is we'll say, all right, well, if we have this given, then we can do some algebra and find this. Algebra is not the focus of this course, right? Geometry is. So if for some reason we have to do algebra in our proof, then we would simply perform all of the algebra as side work and then say, from this equation, I get this because I did some algebra. Simple as that. To clarify a little bit more, we might be given, say, a system of equations, and so we might need to solve that system by substitution. That would be a good idea then, right? Because you can't just say, this is the solution. What you should do is you should take the given and then perform the substitution, right? The second line of the first, right? So this second line, line A, line B is plugged into line A of number 1 to find number 2 here. So this is substitution of 1B into 1A. If you're given something that doesn't immediately substitute, you might have to do some algebra to solve for that variable so you can substitute, in which case you would again appropriately say, you know, I substituted line 2 into, right, that you did some algebra. You might substitute line 2 into 1a to get your new equation, and then algebra gives you the answer. Okay, so there might be a little bit of work to do here based on what's given, but you don't need to show all of the details. You do need to show some. Okay, so algebra itself, you don't need to show. Substitutions, you should show. Excellent. And then the form of theorems. So we talked about conditional statements already, which is essentially we have the situation of an if-then statement. We assume the if, and then we show the then. So our proofs start off with the if x and y are odd integers. If x and y are odd integers, right, that's the given. It's what we start off with. We show the then part. We show the then part is true. So coming back up to here, the then part is x plus y is even, and that's what we finish with. We show that x plus y is even. And what connects those two things is a collection of assumptions, axioms, and previously proven theorems. Okay. So we make statements, and the justifications are the axioms, assumptions, and previously proven theorems. Now, when it comes to a biconditional statement, those are of the form if and only if. It would be P if and only if Q. So if P, then Q. But what these are, is P implies Q and Q implies P. So we have to do two proofs, essentially. We have to assume P, show that Q is true. Finish that statement, and then start again saying assume Q and show that P is true. And that's what's required to show P if and only if Q. So to take a look at that a little bit more specifically, so here's a theorem that says the opposite sides of a parallelogram, right? We want to say that they're congruent, so that the side lengths are the same. So if ABCD is a parallelogram, or no, I'm sorry, ABCD is a parallelogram if and only if AB is equal to CD and AD is equal to BC. So parallelogram A, B, C, D, AB is equal to CD, right? There's no lines here, so those are just describing lengths. This length is equal to that length, and this length is equal to this length. Okay, we have a parallelogram. Well, if we wanted to prove this, we would have to show it two directions, right? We would have to assume that it's a parallelogram and then show that the side lengths are equal. So assume that ABCD is a parallelogram. It's given. We make a statement, we give a justification, we continue on, so 1, 2, 3, 4, up until the last line of the forward direction should be AB equals CD and AD equals BC, right, for whatever justification. So we connected the if part to the then part. Now we have to show the backwards direction. We assume this part, we say that this is given, AB is equal to CD and AD is equal to BC, right? That's given. We make a statement, we give a justification, we continue those manipulations until we end up with the statement that ABCD is a parallelogram, right? We show this direction here, and we show this direction here. Make sure that you clarify which direction you're doing at any given time and restart the count. Excellent. Proofs should always start off with the word proof. If you don't put it all in capitals, that's fine. If you put a semicolon, and yep, so a semicolon is what I usually do. I underline it, lowercase. That doesn't matter specifically, but what you need to do is you need to indicate that you're writing a proof. And I'm not sure why it's on the left side here. Typically, the square is written at the bottom right, and it's filled in. If you just put don't do that, put a filled in square at the bottom right. The reason I say to do that is because this notation matches what we have been doing previously in other courses. So I want it to match as much as possible. Indicate the beginning of the proof, indicate the end of the proof. I need you to tell me when you're done. Not because I don't know, but because I need you to tell me you know when you're done. So please do that. All right, so again, 2-column proof, statement, and justification. We will also see proofs by contradiction. So again, I'm assuming that you've seen these before, so we'll continue to look at these. But when we want to look at a proof by contradiction, we let's see here. Given and assumption are used a little bit differently here. Typically what I do is I assume the things that are given and then use the word suppose. Suppose the opposite of the claim is true. So if I wanted to do, referring back to Theorem 9.1, if I wanted to prove if x and y are odd, then x plus y is even. What I may have done in this case is to, of course, begin by indicating a proof. So x and y are odd. My justification would be that it's given. So this is line 1, line 2. Now for a contradiction, what I'm going to do is I'm going to assume that x plus y is odd. And I'm going to give that as an assumption. And specifically, that's going to be an assumption for a contradiction, so assumption. But what happens here is we make a collection of statements, and let's say here on the 5th line, I don't know how many it takes, we end up with x or y is even. That would be a contradiction. So we would label it as lines. Oh, actually here. We give whatever justification that we need. Here in line 6, we say contradiction. Lines here, x and y are odd, and this one says x or y is even, so lines 1 and 5 contradict each other. And then the 7th line would be thus let's see here, thus x plus y is even. And the justification would be, let's see here, lines 6 and, right, you're saying that there was a contradiction because of our assumption, line 6 and line 2. There's a contradiction, these two lines contradict each other, so we must have that x plus y is even. Indicate the end of our proof. So 2-column proof, thing that we're doing or statement that we're making given by or paired with a justification. Excellent. And that's it for this section. So that was relatively brief. I know that's maybe a little bit longer video, but I didn't see a reason to split it up into 2 videos. If you have any questions about proofwriting, or if you want to see additional examples, we can do those sorts of things during lecture if you're interested, and we'll keep moving on from there. Class should also, or lecture should also have, no, still not what I'm looking for. Content videos should have some examples of 2-column proofs. So as I begin to ask for proofs from you, you should be already seeing examples in the content videos. But again, if you have any questions, ask during class, send me an email, stop by during office hours, or schedule an appointment with me. Lots of opportunity, so please make sure that you're communicating with me if you have any questions. This semester seems to be going well so far. Very thankful for that. But I could be wrong, and if I am, I just need you guys to share that with me. So I'll see you guys later. Have yourself a wonderful day, and we'll pick back up in section 10 in our next video.